everyone. In today's class we are going to talk about system and its properties. So a system is defined as an entity that transforms or processes a set of inputs a set of signals which we call inputs and yields another set of signals which we call outputs. A system may consist of physical components such as electrical and mechanical systems, or it may be an algorithm that takes some inputs, does some processing, and yield outputs. Now, there are some important properties of systems. A system may have memory or it may be memoryless. A system may be causal or non-causal, it may be stable or unstable, it may be linear or non-linear, it may be time variant or time invariant. So we will discuss these properties one by one now. The first property is memoryless system. Memory systems are systems in which the output depends on the current input only. It does not depend on the past input. Typical example is combinational circuits. In the combinational circuits, we know that the combinational circuits are designed using logic gates, using AND or NAND gates, etc. In these systems, output depend on the present input only or the combination of present inputs only. The output did not depend on the past input. So combinational circuits are the example of uh, memoryless systems. For example, another example I have given is the maths equation. As you can have a look, this maths equation, y of n is equal to 2x of n minus x square of n whole square. Because we have n here, so the output is depending on the present input only. Fine. Similarly, y of n is equal to 4x of n, the output depends on the present input only. There is no value of the past. We can also say that a resistor is a memoryless system. Are the systems in which output is identical to input? Of course, they are memoryless systems. Now, what are memory system? Memory in a system implies presence of some mechanism through which a system stores information about the input values of the past. Simply, memory systems are systems which depends on the past value also. Fine. An example is sequential circuit. Sequential circuit, if you remember the flip-flops, in flip-flops the output depended on present input as well as on the previous state. So the previous state is the past input. That is why we say that the flip-flops are sequential circuits, are memory systems. Another example, accumulator or summer, which is a discrete time system with memory. Why? Because it calculates the running sum of all the inputs up to the current time, running sum of all the past inputs and to the current time. So accumulator or summer is also an example of memory systems. A delay system, as you can have a look, a delay system is represented mathematically by this equation. Now we have n minus 1, which means the past value. So it could be n minus 2, n minus 3, n minus 4 depending upon the delay time. So if we have n minus 1 or n minus 2, n minus 3 in discrete time, we say that we have a delay system. Similarly, in continuous time, if we have t minus 1, t minus 2, t minus 3, we say that the system has memory because it is dependent on the past input. Capacitors and inductors are memory systems. Capacitors store energy in electric field, inductors store energy in magnetic field. Another very important concept is causal or non-causal systems. Causal systems are the systems in which the output depends on the present and past inputs. Fine. Output is independent of the future input. Output depends on present and past inputs. There is no future input in causal systems. Output is independent of the future input. Only output is dependent on the present or past or both present and past inputs. So, for example, a delay system is causal. Why? A delay system only depends on the past input. So, it is a causal system. There is no future input in the delay system. Similarly, we have this example, y of n is equal to x of n plus x of n minus 3. We have the present input and we have the past input, which is delayed by 3 units. So this is a causal system because it depends on present and past input. Remember that all memory systems are causal systems. Why? Because all memoryless systems only depends on the present values, only depends on the present input. So they are causal systems. Non-causal systems in which there is at least one future input. So there must be at least one future input in non-causal systems. So non-causal systems are not independent of future value, they are dependent on future value. There is at least one future input in the non-causal systems. For example, this is my equation which represents a non-causal system. As you can look, we have the present input, we have the past input, but we also have the future input. So since there we came across the future input, we say that this system is non-causal system. And there is a subset of non-causal system which we call the anti-causal system. Anti-causal systems are systems that only depends on future values. They do not depend on present or past value, only future value. So for example, y of n is equal to x of n plus 1. This only depends on the future value. So this is an anti-causal system. Remember that it is also non-causal system because anti-causal system is a subset of non-causal systems. So all anti-causal systems are non-causal systems, but not necessarily all non-causal systems are anti-causal systems. Anti-causal systems only depends on future value. Non-causal system has at least one future input. So it can have present or past input in addition to one future input. The third property of the systems is stability. A system is considered stable if its output stays bounded for bounded input. Means that its magnitude does not grow beyond bound. Its magnitude or amplitude does not grow beyond bound. For example, if we integrate a system from 0 to infinity, the answer is some finite value, we say that the system is stable. Fine. Again, if we have some impulse response of the system, and when we increase the time, when we go towards t approaches infinity, the system either approaches 0 or it approaches some constant k, we say that the system is stable. Fine, because it is approaching certain value, it is not growing beyond limit. For example, e power minus 3, e power minus 3, if we plot e power minus 3, we will have a decreasing exponential. Fine. So this is an example of stable system. This is stable system because it is decreasing as we approach to infinity. Fine. And then we have e power 3t. When we go from 0 to infinity, this signal, this exponential signal, which is increasing exponential, kept on increasing. So this is an example of unstable system because it is going towards, it is increasing with time and it's increasing beyond bound. Fine. Other examples could be if we have y of t is equal to a DC value. So if we have y of t, for example 6, which is a DC value, so as you can have a look, because our output is a DC value which is 6, it is not going beyond bound. So this system is a stable system. Fine. If we have y of t, if we have a step signal, y of t is equal to u of t, this is also an example of stable system because it is not growing beyond bound. Similarly, if we have sine of t, sine of t range is -1, between -1 and 1, this is also an example of stable system because we are not going beyond bound. Cosine of t is the other example of stable system. Accumulator, what does accumulator do? It sums all the past values of the input. So if we give it a infinite values, it can grow exponentially if x of n is not bounded. Fine. It can grow to a value beyond bound. It will not stop at the certain value. If we start from minus infinity and keep on adding it, it will not be limited to a certain value. It will grow till beyond limit. So that's why we say that accumulator is an example of unstable system. Other example is a model for the bank account. If there is no withdraw from that bank account, and we have deposited certain amount of money, and then we have compound interest on that bank account on that money. Because of the compounding effect, the bank will grow, at it will not stop at a certain value. It will not stop after 10 lakhs, or it will not stop after 20 lakhs. It will grow beyond bound. There is no set limit for the bank account to be limited, so it can grow beyond uh, beyond limit. Damp oscillation, which is the decreasing oscillation, is example of stable system. Increasing oscillation is an example of unstable system. The fourth very important concept is about linearity. So how we will define linearity? We say that the system is linear if only one condition is met, which is property of superposition, or law of superposition, or principle of superposition, whatever you want to call it. If a system satisfies the law or principle or property of superposition, we say that the system is linear. So this superposition is the necessary but sufficient condition for the systems to be considered linear. Fine. So if a system obeys property of superposition, we say that the system is linear. But if it fails to obey the property of superposition, we say that the system is non-linear. Now superposition has two parts. One is the additivity law, and the other is the scalability or the homogeneity law. Fine. So if a system obeys additivity law and scalability law, we say that the system is linear. So x1 of t plus x2 of t, y1 of t plus y2 of t. This is the additivity property, and this is the scalability or homogeneity property. I will discuss these properties in detail in the next slide. But if someone asks you to give them an example of linear devices, you can always say that resistors, capacitors, and inductors are linear devices. And if someone asks you about non-linear device, you can say that diode is a non-linear device. Other thing is that transistor is linear in amplification region, but it is non-linear in cutoff and saturation region. Like I said earlier, that the linearity of the system is judged upon whether or not it follows the principle of superposition, whether or not it follows the law of superposition, that is, and superposition has two parts, additivity and homogeneity. So first we will discuss additive property. So what we will do is that, for example, we have a system. Fine, we have a system, we want to check whether it's linear or not. So we have this system. Fine, we input a signal, which is the input signal, which is x1 of t. Fine, we get, after the system, after the signal is passed through the system, we get output, which is y1 of t. Fine, then we input another signal, which is x2 of t, to that system, and we get y2 of t as an output. Now what we do at the output is, at the output we sum y1 of t and y2 of t by passing it to the summer. Fine, so we pass it to the summer or adder, which we called it. So when we pass to the output to the summer or adder, of course we will have y1 of t plus y2 of t at the output of this summer, because these two outputs will be added here. So this is, for example, equation number 1. Now what we'll do, this was this first step in additivity property. Remember, there are two steps in additivity property. The first step was, I input a signal x1 of t, get y1 of t. I input a signal x2 of t, get y2 of t. Then the output are added to a summer or adder. So when the output are added, we get y1 of t plus y2 of t, because both these outputs are y1 of t and y2 of t is added. So let this be equation 1. In the second step, what I will do is that x1 and x2, before passing it to the system, remember the system is the same system which we want to check the linearity. The system has not been changed, it's the same system. So first we do is that we feed both the inputs, x1 of 2, x2 of 2, to the summer. So the output will be obviously x1 of t plus x2 of t. Now these two inputs are passed to the system, and we get output, which is y of t. Fine, we get this y of t. If the output is equal to y1 of t plus y2 of t, which we say that is equation number 1, if it's equal to this thing, we say that the system is linear. Fine. But if it's not equal to this thing, the output of this system, we say that is the system is non-linear. Fine, NL, non-linear. So if the output is equal to y1 of t plus y2 of t, we say the system is linear. If it's not equal, we say the system is non-linear. So what we have done to check additivity property, I passed x1 of t to a system, get y1 of t, x2 of 2 to the system, get y2 of t. I add them, get y1 of t plus y2 of t. This is my step 1. And step 2, I add the input signals before passing it to the system. So I add it in the summer, then I pass it to the system. If I get the same result, y1 of t plus y2 of t, we say that the system is linear. If I don't get the same result, the output of the system is not y1 of t plus y2 of t, we say that system is non-linear. This was about additivity property. If y of t is equal to y1 of t plus y2 of t, we say that the system has followed additivity property. Fine. We will check also for the homogeneity property. The second property is homogeneity property. So even if the system satisfies this, it cannot be labeled as linear, because we will also check the homogeneity property. Fine. So this is our first property. The second property is homogeneity property. What we do, that we have an input signal x of t, we feed it to the system. Same system in which we are trying to find that whether it's linear or non-linear. Fine. So we put an input signal x of t, get y of t. Input x of t is the input signal. We got y of t, which is the output signal. Then we feed it to some scalar k. After feeding it to the some scalar k, of course, we will have this value k of y of t. Fine. Now this was our first step. In the second step, what we do is that x of t is first feed it to a scalar. So we first feed the input signal to a scalar, which comes out to be the kx of t. Then we feed it to the system. This system and this system is same. They were also same in additivity property. The system hasn't changed. It's the one system that we want to find whether it's linear or non-linear. So in step 1, we feed the input, got the output, then pass to a scalar. In step 2, the input is first fed to a scalar, output is obtained, output is then fed to the system. When the output is fed to the system, it will have certain output. If that output is equal to k of yt, we say the system has obeyed homogeneity principle. So if the system has obeyed additivity property and homogeneity property, we say the system is linear. Fine. And the final property is time invariancy. What do you mean by time invariant system? If we produce certain delay in input of a signal, and the same amount of delay is produced at the output of the signal, we say that the system is time invariant. Fine. Which means that the time shift in input is equal to the time shift in output. Then we say that the system is time invariant. Fine. So time shift in input is equal to the time shift in output. Time delay in input is equal to the time delay in output. Then we say that the system is time invariant. Fine. It's not that the system does not depend on time. Dependency is a different thing. Dependency is like that the output of the system does not even depend on time. Even if we change the input of the system, if we shift the input of the system to a certain value, the output will have no effect. It's not like that. That's dependency. That's a different thing. This is time invariancy. This means that the shift in input is equal to the time shift in input is equal to the time shift in output. As you can have a look here, we have shifted the input signal by n naught, and the output signal is also shifted by n naught. So we said that this is time invariant system. Similarly, y of t is equal to 3x of t. If I shift x of t is my input, y of t is equal to 3x of t is my output. So if I shift the input signal by t naught, which is, for example, the output is x of t. So if I shift the input signal by t naught, the output will also be shifted. The output is 3x of t, which is y of t. The output is also shifted by t naught, as you can have a look. So this system So this will be t minus t naught, t minus t of 0. This is also my brackets. So you can say the shift in input is equal to the shift in output. So this system is time invariant system. If we have 3tx of t, now the shift will also occur in t, and it will also occur in t of t in x of t. So this is time variant system. And then again, this is also a differentiator, which is also a time invariant signal. Thank you.